using the wooden rod as shown. Then method 1, the dimension of the wooden rod are shown in full size. You have to measure the length and the diameter. So what you will do, you will place your ruler scale and measure this length, and you will measure the diameter. According to paper size, it will be different. But example, say it is 4.5 and 2. This is 4.5 centimeter, and this we are taking as 2 centimeter. Suggest an accurate method for measuring a diameter of a wooden rod. In this experiment, list any additional apparatus that might be required and briefly describe how would you determine the diameter. You may draw a diagram. So how we can accurately measure the diameter as possible, like the diameter of. So we can mention a micrometer, use a micrometer, that's true. Place the wood, that's also another way to place a wooden rod between the two blocks, then measure. That's also a right way. Or you can also, so 2 wooden blocks can be used, or micrometer methods can also be used. So place the wooden rod between the 2 blocks and measure using a ruler the length and avoid a parallax error, or if you can also mention about the micrometer. Then student uses a balance to measure the mass of a wooden rod as shown in figure 1.3. Record the mass of a record mass m of a rod. So already it is directly like example here, which is 7.8 gram, it's written there. Then we have to determine a density, the density of a wooden rod using the values from A1, B, use the equation. Then rho 1 is equals to 4m pi d square L. So all the values are there. So rho 1 is equals to 4. Then the mass, which was 7.8. So multiplied by 7.8 divided by pi, which is 3.14. The diameter was 2.5 square multiplied by length or diameter example we took 2 and the length say 4.5. So when we multiply them, we will get the density, which is about 0.5 gram per centimeter cube. So in paper 6, you don't have to memorize any formula. It will be given. And how to know like what values you have to use. See, if m is there, so it is mentioned m is this value, and d and l are already given in the beginning of the class. The second method, what student did, student pour water into a measuring cylinder as shown. And in figure 1.4, he then floats the wooden rod in a water as shown. And record the value of a V1 of a water level and V2. So use screen annotation to state what are the values for V1 and V2. What is the value V1 and V2? You can use screen annotation to state the answer. So V1 is 144, that's right. What about V2? That's 152. 144 is the right, because each from 140 to 150 there are 5 lines. So each line is representing 2. So that is why it is 142, 144, 146, 148, and 150. So 144 is the right answer. Then student remove the rod and lower a piece of a modeling clay as shown. He then record the volume V3 and V4, and then he used the formula V2 minus V1 over V4 minus V3 into K, and what is the value of a K is 1. So you have V1, V2, V3 and V4, you just substitute and you will get the answer, which will be about 0.57 grams per centimeter cube. Then on a figure 1.8, draw an arrow showing the correct line of a site reading and the volume. So where I should draw an arrow to read this scale accurately. So you can use screen annotation just to mark the position where we should draw an arrow showing the correct line of sight for reading, like where we should place our eye so that we can read it accurately. Yeah, that's right. And you should not draw on the other side. Why you should not draw? If you draw on the other side, you will not score mark. Why? Because the other side there is no marking. The marking is on this side, so you should draw an arrow from on this side. The next one suggests a possible source of inaccuracy in method 2. Even if it was carried out carefully, can you identify inaccuracy in this method? So what might be an inaccuracy in this method? No, for water we always read the lower meniscus. The possible source of inaccuracy in this one, the measuring cylinders are not very accurate. That is one. The raw. We want to measure the volume of the rod, but the problem here, the thread also, when we use this thread, so this thread will also have some volume. So it won't be accurate. It will be inaccurate. And what might happen? The water, like wood might absorb some of the water. So that is also an inaccuracy. So these are some possible sources of inaccuracies for this experiment, like measuring cylinder is not the accurate apparatus. And when we remove, like example, when we remove this clay, some of the water might be removed as well. So there are a lot of sources of, and then we transferred into the measuring cylinder. So this not all of the water transferred into the measuring cylinder. In question 2 suggests students are investigating the cooling of a hot water in a beaker. They are using the apparatus as shown. Figure 2.1 is the apparatus. So what is the room temperature here? What is the value? The room temperature, theta R. So that is 21 degrees centigrade. That's correct. Then a volume of 150 cm cube of a hot water was poured into a beaker and initial temperature is measured. So every 30 seconds, student measure the temperature. Then describe one precaution that you should ensure that the temperature readings are accurate as possible. So whenever we want to record the temperature for this experiment, we should always avoid a parallax error. So we should always look perpendicular, avoid parallax error. And we should keep the thermometer all the time. The thermometer should be at the same location or the same position. When we are measuring a temperature, so we should position the thermometer all the time. It should be placed at same location or same position. Then calculate the average rate of a cooling for first 90 seconds and remaining 90 seconds. So average rate of a cooling, the temperature difference divided by time. So how to find the average rate of a cooling? So for first 90 seconds and then for remaining 90 seconds. So how to calculate average rate of cooling? How much temperature changes? That is 95 minus 79, which is equals to 16. And divided by the time interval, that is 90. And what about the average rate of cooling for the remaining 90 seconds? So from 90 to 180. So how much is the temperature difference is there? That is 10.5 and divided by 90. The formula is given. So we just have to use this formula. Temperature at time is equals to 0. This means temperature at time is equals to 0. This means temperature at time is equals to 90 and divided by time interval. So we'll get the average rate of cooling. So if initially it will be about 0.18 and then 0.12. And it is obvious that initially the rate of cooling is much faster as compared to the later, because initially the temperature of the water is high and rate of cooling is higher at, or rate of cooling is faster at a higher temperature. Then we have to calculate average rate of a cooling from 180 to 270 seconds. So the same way from 180 to 270. So we take a difference here, which is about 6 divided by 90. So this will give us the rate of cooling. The temperature of a water falls as time passes. Use a result from C. Describe the pattern of a rate of a cooling during this experiment. So what is the pattern of rate of cooling? So rate of cooling is decreasing. And how we can say this? You will use the values like rate x1, x2, and x3 are the values for rate of cooling. You'll compare them like x1 is higher and x2 is smaller, then x3 is very small. Give an estimate of the probable final temperature of a water if left to cool for many hours. So what will be the temperature of the water after, like example, 5 hours or 10 hours? So whenever, like example, first we were having a hot water here at the temperature of 95. But when we keep it for like 5 hours or 10 hours, and the surrounding temperature, we calculated the surrounding is 21, but here this was 95 in the beginning. But after 5 hours or 10 hours, it will come in the thermal equilibrium. And what is the temperature of the water? It will be same as the surrounding temperature. So it will be 21. The water will cool down until it reaches a thermal equilibrium, or room temperature and surrounding temperatures are same. So this will be 21 degree centigrade. And a student in another school carried out a similar experiment. She started with the hot water at a lower initial temperature. Suggest how her cooling rates are likely to compare with those calculated in C. So suggestion, what we will say, the rate of a cooling will be smaller. And what will be the reason for that? Because rate of a cooling depends on the temperature as well. Higher temperature, faster rate of a cooling. So it will have a smaller rate of a cooling. And the rate of the cooling depends on the initial temperature. So higher temperature, faster rate of cooling. Suggest one variable other than the initial temperature which student should control. So the other variable which student should control, like she should take the same amount of the water which was taken by the another student in another school, or it should use the same size of a container, same size of a beaker, and same room temperature. So many factors you can mention here. Then in question 3, a student investigating the power supply, he uses a circuit shown in figure 3.1. We have voltmeter, ammeter, and a power supply. Use screen annotation, complete the value for voltage and the current reading. What is the value for voltage and what is the value for current? Each line for voltage is representing 0.1. So 2.1 volts. And what about the current? Each line is representing 0.02. So 0.26. Then we need the resistance. So we'll divide voltage divided by current. We'll get the resistance, which is for 100 centimeter. Then student record the resistance. Length is there, current, and 1 over current, reciprocal of a current. Calculate and record in the table 1 over I for 70 centimeter wire. So 1 over I means like 1 divided by 0.35. So it will be 1 divided by 0.35 will give us the value for current, which is 2 point, reciprocal of current 2.86. Then we have to sketch a graph, and they already mentioned we don't have to include the origin. So if we don't have to include origin, no, don't include that. You can, like for length, it is starting from 30 to 70, like the range is there, and for one reciprocal of a current, it is 1.54 to 2.86. So I can start, like example, from 1.5 to 3, and this I can start with 30 to 70. Then you will plot a graph from the reading above. And from your graph, you'll determine the gradient, y2 minus y1. So it will be a straight line, not necessarily starting from origin. It will be a straight line. Take 2 points, y2 minus y1 over x2 minus x1 will give us the gradient. And gradient, you will how to find the value of E? E is equals to gradient into R0 divided by K. Gradient is there, that you already will calculate from the graph. R0 is the original resistance, which we calculated, and K is 100. So this will give us value of E. Then ammeter in the circuit has a smaller resistance which affects the current. The effect of this resistance on the measurement of current I will be different on each measurement, measured length L of resistance of wire. State and explain which length will be the most affected by the resistance of ammeter. So they already mentioned ammeter is having a low resistance, and if you are using shorter length, so shorter length will also have low resistance. So if you are using a shorter length, so low resistance, both will have low resistance. As a result, the most likely the ammeter, the current will be affected is for a length of 30 centimeter. Why for a length of 30 centimeter? Because they already mentioned that ammeter in the circuit has a smaller resistance, which affects the current. So the effect of this resistance on the measurement of a current will have a different measure for the length. So when the length is shorter, so statement, it will affect 30 centimeter length, because resistance is proportional to length. So when we have a shorter length, it will have low resistance. The wire will have low resistance, so ammeter resistance will affect the circuit as well. So this was from Feb Mar